And here today, we're going to do 11.1 and 11.2. Be 30, 40 minutes probably at most. Okay? So, in your mathematics career, right, when you're in like first grade kindergarten, the first thing you learned was like addition. And right after it, you learn subtraction. Why do those two come in a pair?
Because they're together in the
But what is their relation? Okay, that's true. What is their relationship with each other, though? One undoes the other, right?
Yeah.
Okay? You get to like third, fourth grade, you start learning multiplication, and then at the same time, you're going to learn division right after. Why do those two come in a pair? Because one undoes the other, right? You get to algebra 2. You talk about exponential functions. What comes right after that? Logarithmic functions. Why? Because one undoes the other, right? This is a common theme throughout all of your high school and elementary school mathematics education has been we introduce one operation and immediately follow that we have the undo operation. Everybody's okay? In chapters 9 and 10, we were talking about the derivative. What we're going to do in chapter 11 is introduce the operation that undoes the derivative. Okay? So that process of undoing a derivative is called antidifferentiation. And the operation, the symbol that undoes that process is called the integral. So, for example, remember that our derivative shortcut for a power function, the derivative of a times x to the n, is n times a x to the n minus 1. You guys remember that? So, for example, if we have the polynomial 3x squared plus 4x plus 5, and we differentiate that, we get 6x plus 4. Everybody gets good? Remember all that from last chapter? What we want to do is be able to take that 6x plus 4 and then recover the 3x squared plus 4x plus 5. Okay? That recovery process is called antidifferentiation. So far, so good? Just trying to like beat in some vocab into your brains here so that when we hear some words, you understand what it is that we're doing. So symbolically, what that looks like is we're going to have this integral symbol, which looks like kind of a stretched out letter S. That's not an accident. We'll talk later in later chapters like what this integral operation is really doing from a like a fundamental like theoretical background conceptually what this is doing. And really what it's doing is kind of like a summation. So the reason that integral symbol looks like an S is because of what you're really doing is like summation. So you're adding a bunch of things up. We'll talk about that later on in the chapter, kind of how that actually is working, like the machinery behind this operation. But the formula that you need is that if I want to find the antiderivative of ax to the n, I'm going to add 1 to the exponent and then divide by the new exponent. Just like to do the derivative, we multiply by the exponent and then subtract 1 from the exponent, right? Everybody's okay there? Here we're going to be adding 1 to the exponent and divide by the new exponent. And we do that for all exponents except for -1. Which we won't ask you to be able to do by hand. But oddly enough, if you're interested, the antiderivative of x to the -1 is the natural log of the absolute value of x, unexpectedly. It's like, whoa. All right. So an observation here So notice that if I take the derivative of 3x squared plus 4x plus 2, and I take the derivative of 3x squared plus 4x plus 5, I get the same result, right? Both of them are both 6x plus 4. And if I try to then take the integral of 6x plus 4, I would add 1 to the exponent and then divide by the new exponent. And then really on 4, it's like 4x to the 0, right? So it's going to be like 4x to the first. So when I do that, I end up with 3x squared plus 4x. But notice, is that the same thing as what we would have started with? Have we actually recovered the original? No, man. What's different? There's no plus 2, right? Notice that if I try to integrate 6x plus 4 that came from 3x squared plus 5, I'll get the same thing, right? If I'm integrating, again, you notice that we're missing that constant term at the end. That piece is unrecoverable. So what we do to kind of account for that is we just write plus c at the end, where that plus c represents some constant that we actually can't recover. Everybody's okay with this? So when we have the plus c at the end, we call this the general antiderivative. And the process of finding that general antiderivative, we say that this is then an indefinite integral. So just kind of throwing some vocabulary at you. Is everybody okay with the names that we're given these things and these processes? It's really important that you know the names and know what you're being asked to do so that when you read directions on a test or quiz or an IB exam, you know what, like, oh, that's all it's asking me to do. Because there's lots of different ways that they might ask you to do that. All right. Let's go and just do some practice now. So we're not going to do all of these. I'm just going to we'll pick a couple. Sound good? So the directions ask, find each antiderivative in general form. So when I see general form, I know that that's going to mean that every answer has a plus c at the end. Okay? Easy place to lose points is just for getting plus c's when you're supposed to put them there. Let's try to make sure we do a good job on that. All right. Maggie, pick a letter from A to J. A. So remember, our formula for our antiderivative is this, right? So we're going to have the 4. That's like my A. My variable is t. Its exponent is 1, so I'm going to add 1 to the exponent and then divide by that new exponent. And when I reduce, then I have 2t squared plus c. You guys feel okay on that? All right, let's do another. Henry, what's your favorite letter here? J. Okay, so J's a tricky one. And the reason J is tricky is that if I look at the thing that I'm supposed to be integrating, this x plus 200 divided by x plus 4, it's not written as a power function, right? So I'm going to need to do a little bit of algebra to rearrange that thing that I'm supposed to be integrating before I can integrate it. So I'm going to write that compound fraction as two separate fractions, each with a common denominator. And then I'm going to reduce those fractions and rewrite them with negative exponents. So x divided by x to the fourth should be 1 over x cubed, right? If I write that with a negative exponent, we'll just write that x to the negative 3. And then 200 over x to the fourth should be 200 x to the negative fourth. So far, so good. Now, if I look at each of these things, now they're each written as a power function, so I can use my rule for integration. So for x to the negative 3, I'm going to add 1 to the exponent and then divide by the new exponent. For 200x to the negative 4, I'm going to add 1 to the exponent, divide by the new exponent. So that's going to give me x to the negative 2 over negative 2 plus 200 x to the negative 3 over negative 3. And then I'll put a plus c at the end. And this answer is acceptable, although if you're looking in the back of the book, they probably are going to write it like this. But the above answer is fine, unless the directions specifically say write it without negative exponents or something. Those two answers are equivalent. I would give either one full credit without any bias. What do you guys think? This should be fairly straightforward, right? Does it remind you very much of just like doing the derivative? Yeah, it's just basically the same idea, just backwards process, right? Okay. Do you guys want to do any more examples of this? You feel like I'm all right? You got it? All right, keep on moving. So here it asks us to find the antiderivative of f prime of x equals yada, 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 when f of 1 is equal to 6. So notice the find the antiderivative piece. We know what to do there. This piece, though, what is this going to be for? Notice that it doesn't ask for the general antiderivative, so there should be no plus c in this problem. It wants the actual value for c. That's what we're going to use f of 1 equals 6 to find. Okay? So that part is just going to be used to find c. So f of x should be the integral of 3x squared plus 4x plus 5 So that is written in a form where we're ready to do the antiderivative to it. So I'm going to add 1 to the exponent and then divide by the new exponent. Add 1 to the new exponent, divide by the new exponent, add 1 to the new exponent, divide by the new exponent, and then I have a plus c. So when I simplify, I get that. So far, so good. Now, if I know that f of 1 is equal to 6, I know 6 is equal to 1 cubed plus 2 times 1 squared plus 5 times 1 plus c. Oops. So when I subtract the stuff over to solve for c, I get c equals -1. And that gives me then my final answer. And I'm done. So notice that this problem is really no more difficult than the previous problem, and we just add an additional step at the end where we have to solve for c. But again, if you're given the x and the y, all you're doing is plugging in x and y and solving for c. Does everybody feel okay as to what we did there? Lucy, you're making faces. Are you good?
I think so.
Okay, just checking. We call this is when we give you a point like this is called a boundary condition. But all it is like basically I'm giving you a point on the original function that you can use then to solve for the plus c at the end. So we can give that an actual value. Okay? All right. Do you guys feel okay on that, or do you want to do one more example? You got it? Okay. That's fine. Let's do this one, though. Okay. Oh, it's not gonna, okay. We'll just do it off up here. It says a factory has modeled the marginal cost of producing sunglasses as C prime of n equals 45n squared minus 130n plus 80, where C prime of n represents the additional cost in US dollars for an additional pair of sunglasses, and n is the current production level of sunglasses per month or production level in thousands of sunglasses per month. I'm out. Yes. The factory is currently producing 1,000 pairs of sunglasses per month at a cost of 50,000 US dollars. So let's do, you guys, does anybody taken the SAT this year or in the past? Last year. Okay, perfect. On the SAT, on the verbal section or whatever, do they still do those analogy problems like good is to bad as rich is to? Yeah? Okay. In that case, for my good is to bad as rich is to poor, probably, right? You'd expect. Okay. I'm going to make a similar analogy here. So derivative is to rate as integral is to accumulation. Okay, so when we think about derivatives, what you're doing is generating a rate. When you're thinking about an integral, what you're doing is accumulating stuff. Okay, so the easiest analogy I can make here is we talked about position, velocity, and acceleration as all being derivatives of each other, right? If I integrate velocity, what I'm doing is I'm accumulating distance, giving me a position. right? Or if I'm integrating acceleration, what I'm doing is accumulating that acceleration, that rate, and generating a velocity. Does that feel okay here? So if it's asking us to oh, it doesn't ask us anything. Well, if it asks us to find like how much it costs to produce the 1,000 anyways. So if I'm looking to generate a cost function, what I need to do is integrate its rate function, right? Because then a cost is the accumulation of how much it costs. The total cost is going to be like an accumulation of how much it costs to produce each item, right? And that's exactly what the marginal cost is. So what we're going to be doing is integrating our marginal cost so again, we just add 1 to the exponent and divide by the new exponent. I think this will be the last example where I write out like me doing these adding ones and dividing by, like after this example, I'm just going to start like doing it quickly in my head because I suspect that we are probably comfortable with whole number addition and division, that I can say that's what I did and you guys will just believe me. So we simplify and reduce. So this is my cost function. And then it tells me that the factory is able to produce 1,000 pairs of sunglasses for a cost of $50,000. So the only catch here is that the IB loves to do stuff like this. So notice that they're what is N representing? So it says N is the current production level in thousands of sunglasses per month. So if we're producing 1,000 sunglasses per month, what is N? 1. Notice if you plug 1,000 in, you're going to get a vastly different answer, right? Okay, so if we know the cost of 1,000 sunglasses is 50,000, I basically just plug in then, to solve for C, and whatever that comes out to be, let's see, that's negative, so 30. So I think that's what I get. Is everybody okay with the story problem version? Again, the hardest part there was making sure you read it carefully and observed that N is 1 instead of 1,000 when you plug things in, which I think, again, is like just like a lousy trick, but like the IB loves their lousy tricks, as you've probably noticed from other IB classes you may have taken. All right. So we talked in section 11.1 about the indefinite integral, right? And the only thing that separates, or the thing that really illustrates the indefinite integrals, we get these plus c's. What we're going to do in section 11.2 is we're going to look at something called a definite integral. So the visual of the definite integral is going to look a little bit different because we're going to have a number written at the top and bottom of our integration symbol. We call those the bounds of integration. The number at the bottom of the integral symbol is called the lower bound, and the number at the top is called the upper bound. Hope that's not surprising. So what we do with the definite integral is we do our antiderivative as usual, but there's no plus c. Instead, what we're going to do is we're going to write like a vertical bar, and we're going to write those bounds of integration at the bottom and top of the bar, just like they were on the integral symbol. And then we're going to plug those bounds of integration into our new antiderivative formula and subtract them. And it'll always be upper bound minus lower bound. And the result we're going to get is just a number. So when we do the integral, we do an indefinite integral. The result is a function, it's an equation. When we do the definite integral, the result is a number. Just like when we took the derivative of a function, we get a function. If we look at the derivative of a function at a point, that is a number. Okay? So just kind of like that. All right. So we got a couple of examples. We'll do one or two of these to make sure we got the hang of things. We got letters A through E. Lucy, what's your favorite letter here?
E.
E. Okay. So we're going to start by writing the formula for the antiderivative with no plus c. So I add 1 to the exponent and divide by the new exponent. I'll draw my vertical line, write my lower bound on bottom and my upper bound on top. Any questions as to how I generated that antiderivative? Okay. Now we're going to plug in the upper bound into that function and then subtract by the lower bound plugged into that function. Okay, so I got 64 over 3 plus, oops, that's supposed to be a squared, plus 10 minus 8/3, oops, plus 8/3 minus, straight, I'll write this way, minus a negative, and then minus 5 over 2. So that's going to be 72/3 plus 10 minus 5 over 2. 72/3 reduces to 24. So I have 24 plus 10 minus 2.5, so that's going to be 31.5. Is everybody okay with what we did there? Now I'd like to point out to you that while your graphing calculator can't do an indefinite integral, it can do a definite integral. So if you have your graphing calculator with you and you'd like to follow along, or if you want to follow along and don't have yours, I have calculators on my desk. You're welcome to borrow one. So just like we can do a derivative at a point on our calculator, we can do a definite integral on our calculator. So to do that, I'm going to start by pressing the math button. And then I want command 9 that says fnint, that stands for function integration. And now I'm just going to type in the problem, just like it looked like on my sheet of paper. I forget what the problem was. Go back and look here. 8x squared plus 5x. Thank you. So basically, I just type into my calculator exactly like it looks like on my sheet of paper and press enter, and out she spits. On the IB exam, there'll be problems where you will not be able to do the integral by hand, where they'll expect you to know that I can do this definite integral on my calculator, because they're going to give you stuff where it's like you just don't know the integral rules on how to do it. Or there could be situations where like nobody knows how to do it. Now, in general, in calculus, differentiation is the easy part. You can write down basically any function, and we have rules for how to do the derivative of it. Like that's totally doable. Not the case with integration. So integration, there are integrals where there is no antiderivative formula that exists to track backwards, where you have to do it by like approximation methods. And there's like whole branches of mathematics that study these things. Anyway, nope, that's not what I want up. Yes. All right. So let's look at one last example, and we'd be done here for today. Right at probably 40 minutes per my estimate. Good job, Mr. Kulik. It says a tank containing 10 cubic meters of water is draining. The change in water volume is given by dV dt equals yada, 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 where t is in minutes since the tank started draining. Find the change in the volume of water in the tank in the first 3 minutes. So what we're looking to find here in part A is the accumulation of how much water is leaked out of the tank. Does everybody see from the verbiage why we're talking about an accumulation here? So that if it's an accumulation, we want an integral. And the rate at which the water is draining is this. I'll just write the numbers. That. And if we're talking about the first 3 minutes, we're talking about from minute 0 to minute 3 that we're accumulating over. So those will be the lower and upper bounds for my definite integral. And I could do this one by hand, but like, shoot, Mr. Kulik, we got the graphing calculator. Might as well practice using that. So I get negative 1.491. And this was measured in cubic meters. Says then find the amount of water that drains in the time between 4 and 8 minutes since the tank has started draining. Well, shouldn't that just be the integral from 4 to 8 of the same thing that we just did? Yup, it will be. Well, that's wonderful. That's super easy. So that's negative 1.952. And actually, we should probably say this is, positive and say they're lost. 1.9, oh, I forgot the number now. 52, okay. Right, we don't water volume shouldn't be a negative number. We should just add a verb at the end that indicates why the number's negative. So far, so good. Now it says find the time in which the water is empty, or the tank will be empty. How much water do we need to lose for the tank to be empty? Well, it started at 10. So we need essentially the equation to be that, right? So far, so good. So I'm going to go ahead and do my antiderivative. Oops. And then we'll go ahead and actually, I'll reduce that fraction as long as I'm at it. So far, so good. What I'm left with is a quadratic equation, right? To solve the quadratic equation, I have lots of different methods. On the IB exam, probably what I would do in this situation, in the interest of time, would be to just use my calculator to graph this. So again, I have 0.001x squared minus 0.05x plus 10 equal to 0. So far, so good. This is a time that we're solving for. We saw from 0 to 3, we lost about 1.5. From 4 to 8, we lost another 2. So that right there over, well, it's not quite 8 minutes because we didn't account for minutes 3 to 4. But that's like 3.5, so maybe 4 over the first 8 minutes. So it's going to be a little bit more than 8. So I'm just going to make this like up to 30 or something. That should more than cover it. And I'm just going to hit graph and look. Oh, look there, looky there. So second trace, looking for that 0 command, enter, enter. So at basically 20.87 minutes. And if I really wanted to, there should be a second solution to this somewhere. So if I just like really kind of zoom out here a bunch, I can probably see that, although I think the second solution is going to be like a nonsense value. Okay, so it's going to be way out here somewhere. I wasn't expecting that. Oh, it's going to be way out there, huh? There it is. But here's the thing, like, once the volume is negative, does this problem make any kind of sense anymore at all? Nope. So the second solution over here is like complete utter nonsense, right? I'm just looking for that first one that occurred. And that's all she wrote here, dudes and dudettes. What do you guys think on this? Not so bad, right? Very much in fitting with the previous chapter, I think. So these all 9, 10, and 11 all fit really nicely together and feel like kind of all doing the same thing, because it's kind of that way. I'm going to stop here for today. You guys can choose to work on the part of the problem set here from 11.1 and 11.2 that you can see on the board. That assignment won't be due until next Sunday at midnight. So nothing, I think, is due this Sunday because we had the test and had already collected everything from chapters 9, 10, and 11, right? I think everything was already due from those chapters, or from 9 and 10, not 11. Haven't done 11 yet. Okie doke, artichokes. Okay. Be productive.